this is the video lecture series of real-time operating systems. We are going to discuss about the inter-process communication and synchronization mechanism, which is called Semaphore, in this video. So we'll be mainly discussing on the introduction to Semaphore. Also, we'll be discussing the critical session problem, which is a very important topic in RTOS. And for finding a solution to this critical session problem, we mainly use Semaphore. Okay. Next, we also discuss the types of Semaphore, and another important type of Semaphore is actually Mutex. We'll be also discussing about that. Let us move on to our video. So, what is a semaphore? Semaphore is actually a variable, or it is an abstract data type, which is used for the communication and synchronization between various processes when they are trying to access a common or a shared resource or a variable. Consider that there is a shared resource or a shared variable is present there, and multiple processes are trying to access this shared resource or variable. Okay, so when there is a sharing of any resource or variable, there can be a synchronization problem or a communication problem, right? So in order to avoid these problems, we can make use of a semaphore, which you can consider as a variable or a abstract data type, which is actually performing this synchronization mechanism or communication mechanism. We'll discuss about this in detail after discussing the critical session problem. Okay, so the next topic we are going to discuss is actually a critical session problem. So we are going to discuss this critical session problem with the help of a small example of a banking transaction. Okay, so consider that there is a bank account and there is a variable of bank balance. We all know that there is a bank balance and it is represented by some variable, right? Now, consider that you are going to read your bank balance. That is, you are going to read that variable. So, while you are trying to read that bank balance variable, somebody has tried to deduct an amount from your bank account. Okay, so if these two processes are happening at the same time, that is, you are going to read that bank balance variable, and at the same time, if somebody is deducting an amount, means the value that you are reading or the bank balance that you're obtaining will be an error value, right? So this section of the code is actually a critical session. Means there is a shared variable here, which is your bank balance variable. Okay, so this shared variable, whenever there is a shared variable or a resource in a particular segment of a code or a program, that section is called a critical session. Means if that section is accessed by more than one process, okay, and that session is a critical session. Means if any of the process is trying to modify that variable, there can be a change in that variable, okay, and the actions that are performed in the critical session has to be atomic. Means at a time, only one process can access this session. That is, when you are trying to read your bank balance, only the reading process has to access. If the deduction is happening or if the deduction process is accessing, means there can be an error. Okay, if both the things are happening at the same time, or if both the process are trying to access this shared variable at the same time, means there can be an error value. Okay, so this type of codes, I'm just taking an example of banking transaction. There can be other examples also. Okay, so just like that, there is actually a lot of other examples in which some shared resource or some shared variable is involved, and that segment of code which is having a shared variable or a shared resource is called a critical session of code, and the actions that are performed in that critical session of code has to be atomic. Atomic means only one process can access that code at a time. Otherwise, the reading and writing, all these things can be erroneous. Okay, so this type of coding or this segment of code is called a critical session. Now let us see some properties of the critical session. So this is actually a like a representation of a critical session. This red color is a critical session area, and this critical session is guarded or controlled by two other sessions, which is entry session and exit session. And also there is a reminder session also. Now various processes are actually trying to access to this critical session, and this process are controlled and coordinated with the help of this entry session, which will be actually permitting only one task or one process to enter the critical session. Otherwise, just like the example that we have discussed now, there can be problems. Okay. And when a code is exiting this critical session, then another process can try to enter the session. Just like that, there should be a synchronization mechanism between various processes. Okay. Because this critical session is very important, because multiple tasks or multiple process is trying to access it. So there need to be a coordination between this accessing. Okay. Next, let us see some properties, not just solutions. These are actually some properties of the critical session. First one is mutual exclusion. Mutual exclusion is the thing which we have discussed till now. Means when one process is accessing the critical session, other process has to wait. All the process cannot access the critical session variable or a critical session code at the same time. When one process is accessing, the other process has to wait. Next, progress. Progress means if one process is not accessing the critical session, means it should not block or it should not prevent the other process from accessing it. Or in simple words, if a critical session of code is untouched, or if it is not being used by any process, then any process is free to access it. Okay. If it is not being used, means any process is free to access it. Next, another important point is bounded wait. Okay. So bounded wait means, consider that a process was trying to access the critical session, but it is being used or it is being accessed by some other process. So the process which is trying to access the critical session should wait for some time, and that wait should be bounded. Bounded means it should not wait for an endless period of time. It should not wait that is without any time limit. It should wait only for a particular period of time. After that, if it is not getting the critical session, means it should do something as a remedy to it. Rather than just keeping on waiting, it should do something instead of it. Okay. If a process is trying to access the critical session and if it is going on waiting, means there are chances that the process may get blocked. So this blocking should be prevented. So the wait should be bounded. Okay. Next one, let us try to discuss in detail about semaphore. So that is actually the most important topic that we are going to discuss in this video. So semaphores, so we have actually discussed that what is a critical session, right? And in order to have a synchronization for various processes which are trying to access this critical session, we are using the semaphore. Semaphore is actually a synchronization mechanism or a communication mechanism between these processes which is trying to access the critical session. Okay. Now let us take another example here. There is a real life example to understand the concept of semaphore. Consider that there is a bike. Okay. And there is one key for riding the bike. Now if one person is using the key, and if he is riding the bike, means the other person cannot ride the bike, right? Because the key is being used. So the first person, he'll take the key and he'll ride the bike. And after that person has finished off, or if has finished riding, that person will give the key to the other person and then he can ride the bike. Just like this key, the semaphore will act as a synchronization mechanism between various processes. So the bike you can think of as a critical session, and the semaphore will be acting as a key to the critical session. Okay. So the critical session is accessed by the variable or the key which is called a semaphore. In order to access the critical session, you require a key or you require a variable which is called a semaphore, and that acts as a synchronization or a communication mechanism for various processes. So just if you are not able to recall the definition, just understand this concept or this example which I have given to you, which is the example of a key and a bike. Okay, bike you can think of as critical session, key will be the semaphore. Now there are three types of semaphores here. Binary semaphore is there, counting semaphore is there, and mutex is there. We are going to discuss about one by one. First one is binary semaphore. This binary semaphore is having values 0 or 1. Normal case, when the semaphore is not being used, that is the key is not being used by anyone, or if the semaphore is untouched, or if it is not used by any process, its initial value will be 1. And the state of that binary semaphore will be the available state. And if any process is trying to access this, that is if any process is accessing the semaphore, means it will be in the unavailable state and its value will be 0. Okay, this is the normal case. There can be the reverse case also. Initial value, that is initially it will be in the unavailable state, and if any process is releasing it, it will be moved to the available state, and then its value will be equal to 0. It can be in any case. Normal cases, initial value will be 1. When one process is accessing the semaphore, it will move to the unavailable state and its value will be 0. Now here one property of the binary semaphore is that, consider that a binary semaphore is having initial value 1 and a process has accessed it. Any other process can release this binary semaphore. Okay, so it will just act as a synchronization mechanism or a communication mechanism. So it can have two values, 0 and 1. Initially its value will be 1, and when one process is using this key or using this semaphore, it will move to the unavailable state and its value will be changed to 0. And from the unavailable state, it will again move to the available state if any other process is releasing it. Okay, so here there is no such condition that only if a process is accessing this binary semaphore itself has to release it. Any other process can also release the semaphore. Okay, next one, which is counting semaphore. Now, in order to understand this counting semaphore, again we can take a small example of a room with multiple number of keys. Okay, consider that there is a room with multiple number of keys. Means more than one person or more than one process can access this semaphore. Okay, so we'll go back to our example. So there is a room with multiple number of keys. So more than one person can enter the room, and till the nth number of key, that much of persons can enter the room. Just like that, the counting semaphore is also having a count. Okay, so there will be a initial count here, and multiple process will try to access it. So it can be accessed till the nth number or till the count value is completed. Okay, so when the count is 0, what will happen? Now further nobody can enter the room because the count or the key has, all keys are being used now. Okay, so just like that, here the counting semaphore is also having a count, and it can be accessed multiple times by multiple process. And when all the values or when all the keys has been finished, it will move to the unavailable state. Okay, so this is called a counting semaphore. Initially it will be in the available state, and this accessing will keep on going till the count is equal to 0. When the count has become 0, it will move to the unavailable state. Here also, just like a binary semaphore, if a process is accessing it, any other process can release it. Okay, here also this counting semaphore will act as a key to a critical session, but the critical session will be having more than one shared variables or more than one shared resources. So more than one process can access the critical session, because till the count, that much of process can access this critical session. That is the feature of the counting semaphore. So with the help of a counting semaphore, a critical session can be accessed by more than one number of process. That is, till the count, that much process can access the critical session. Okay, so that is a counting semaphore. Next type of semaphore is a mutex. So this mutex is actually like a binary semaphore itself, but it is having one property. The binary semaphore, if one process is accessing it, another process can come and release it. But here, for the case of mutex, it is having a very important property called principle of ownership. Means if one process is accessing that semaphore, which is called the mutex, only that process can release it. No other process is able to release it. So this property is called principle of ownership, and this makes the mutex a very peculiar type of semaphore. Means consider that this mutex is accessed by a process and it has entered the critical session. Only when that process is releasing the mutex, the other process can access it and can enter the critical session. Okay, so this is a very important property of mutex. Next, let us have a comparison between binary semaphore and mutex. Now, the binary semaphore, it is based on the signaling mechanism. Next one, it is based on the locking mechanism. Signaling mechanism means just used for synchronization. When one process is accessing it, the other process can come and release it. But again, there is a synchronization happening between them, right? Here, there is a locking mechanism. So with the help of a mutex, a particular process can lock the critical session. Means only when that process is interested in releasing the mutex, the other process can access the mutex and can enter the critical session. So there is a locking happening with the help of the mutex. Now, the thread which is having high priority than the current thread can also release the binary semaphore and take the lock. So this thing we have already discussed here, but only when a particular process has accessed it, only when it is releasing the mutex, it will exit the critical session and other process can access it. Okay. So the semaphore value, next let us discuss the other property of binary semaphore. The binary semaphore value can be changed according to wait and signal operation. Now mutex values can be modified just as locked or unlocked. Okay. So there is a locking happening in the mutex, but here wait and signal, these are the two operations. Now multiple number of threads can acquire the binary semaphore at time concurrently. Here only one thread can access it, only that can release it also. Then only when it is released, the other thread can access it, then that thread has to release it. Okay. Next, binary semaphore has no ownership, but here for mutex there is a principle of ownership. Now, for the case of binary semaphore, they are faster. Here they are slower. Why? Because if a particular process or a thread, if it is not interested in releasing the lock, means there can be a time delay. The other process has to wait for longer period. Okay. So there can be a waiting time more, but here they can be, that is this binary semaphore operation will be faster. Now next property, if you have number of instance of resource, it is better to use binary semaphore. Now if there is only one instance of resource, then it is better to use mutex. Consider that there is only an exclusive resource. In order to have a synchronization for that resource, you can use mutex because one process will come and access the mutex and will use that critical resource. And when that process has finished off with its usage, then it will release the mutex, and only then the other process can be, other process can access that resource by further accessing the mutex. Okay, so this property called a principle of ownership is very much important for the case of mutex. Next, let us discuss some advantages of semaphores. Semaphores are machine independent. Semaphores are implemented in the machine independent code of microkernel. Now, they do not allow multiple processes to enter the critical session. That is the main function or usage of semaphore. They can be used for inter-process communication and synchronization, mainly synchronization. Okay. As there is a busy waiting in semaphore, there is no wastage of process time and resources. There is no time wastage here because mostly what happens is that when a process is coming and trying to access a semaphore, when it is not free, it will wait. Okay, so there is no time wastage. They allow flexible management of resource. That is the biggest advantage. Now the disadvantages are, one of the biggest limitations is priority inversion. Now let us take the case of mutex itself. Consider that a low priority thread has accessed the mutex and it is using the critical session. Now at that time, a high priority process has come to access the critical session. But what happens is that since the mutex is unavailable, the high priority process will be going to a waiting state, because we all know that Mutex is having a property called principle of ownership. Whether it is a low priority task or a high priority task, that task itself has to release it. Okay, so the high priority task has to wait until the low priority task is releasing the Mutex. So there is a priority inversion happening here, because when a high priority task is waiting, a low priority task is using the critical session or has gained an access over the Mutex. Next, operating system has to keep track of all calls to wait and signal semaphore. Next, in order to avoid the deadlocks in semaphore, means this waiting, unlimited time of waiting. The wait and signal operations required to be executed in correct order. Otherwise, there can be a condition that some process will go to a endless waiting period. Okay. Another problems is that they are more prone to error, and deadlock problems can also happen. And another important problem, the programming of semaphore is complicated. You have to correctly program it. Otherwise, there can be deadlock or unbounded waiting can be there. Okay. So that's all about this video. We have actually discussed about semaphores. We have covered mostly all areas of semaphore session. We have discussed what is a binary semaphore, what is a mutex, what is counting semaphore, all these things we have discussed with the help of state diagrams. Okay. So if you are going to write your semester exams, mostly focus on the state diagrams. If you draw the state diagrams itself, you'll get more than 60% of the marks. So that is a guarantee thing. So focus more on the diagrams and other things, and focus mainly on the keywords like priority inversion and principle of ownership. These things you have to mainly focus on. So this is actually very important area of real-time operating systems. Even if you're going for interviews, this question will be there. That is, if you are attempting questions from RTOS, this question will be there for sure. Okay. So I'm really hoping that the video was useful. And if yes, please do give it a thumbs up. Also share this video with your friends. And if you want more videos, please do subscribe to the channel. Thanks for watching and keep on watching.